Okay, hi everyone. Welcome back we're now past the halfway point, week 6 of CS224N. And so let me just give a couple of quick announcements first. So today is the day that you have to have done the mid-quarter survey by. Hundreds of people have, but if you haven't, this is your last chance to get the half point for that. Today is also the day that final project proposals are due. We really encourage you to try and hand them in on time or nearly on time. That's really just to help you so we can more quickly give you feedback on final project proposals. And in the background, then there's also assignment 5. You'll have seen the message that we're giving you 1 extra day for that, but we do certainly encourage you to be hard at work on assignment 5 at this point. Hopefully it's a great, exciting opportunity to be learning all the latest stuff about transformers. And then today, I'm delighted to have our first invited speaker. Let me just mention that going along with invited speaker, half point of participation credit is you guys writing a reaction paragraph talking about something that the speaker talks about, and there are instructions up for that on Ed. But without further ado, let me introduce Danqi Chen. So Danqi is one of the foremost researchers in question answering, and she's particularly well known in recent work for being one of the co-authors of the Robustness paper, the BERT paper, and on using dense passage retrieval methods for open domain question answering, and is a professor at the Princeton University. But as one other comment, Danqi once upon a time was the head TA of CS224N. So she's quite familiar with the context of this class. So I'm really delighted to have Danqi here to give this lecture on question answering. Thanks.
Thank you, Chris, for the introduction. For me, it's a great opportunity for me to come back to CS224N today and give this lecture, although being virtually. So question answering is an area that I have been working quite a bit in the last few years. So today I'm very happy to introduce you some of the fundamentals in this field, as well as some cutting edge and state-of-the-art topics. So here's my plan for this lecture. So first, I will give a brief introduction of what is question answering and what kind of problems that people are starting today. Then I'm going to spend the most of this lecture focusing on one type of question answering problems called reading comprehension. So this is basically the problem of how we build systems to answer questions over a single passive text. So I know that many of you are going to do a default project on the Stanford question answering dataset. So understanding this part will be very crucial for your final project. So at the end of this lecture, I'm hoping to spend hopefully 20-ish minutes to talk about a more practical and, in my opinion, a more exciting problem called open domain question answering. So basically try to answer questions over a very large collection of the documents. So my plan is try to quickly go over some of the state-of-the-art methods in this area. Okay, so let's just get started. So first, what is question answering? So the goal of question answering is to build systems that can automatically answer questions posed by humans in a natural language. Question answering, or let's say QA in short, is one of the earliest NLP tasks. And the early systems can even date back to the 1960s. So here is one example of the early, one of the early QA systems in back to 1964. So as you can see that this system is trying to answer a question like what do worms eat, and then finally return from the answer that's the grass. So to do this, so this system is basically trying to find some kind of text matching between the question and some kind of text segments, and by using some kind of dependency analysis. I assume that you have already learned the dependency parsing in this class. And there are many different types of the question answering problems. And we can categorize all these question answer problems based on either the information source or the type of the questions or the type of the answers. So for the information source, we can build a system that can condition on short text text, or a very large collection of the documents, or even like structured database or structured knowledge bases, or even tables or images. So for the question type, we can also build systems that can answer like factoid questions or non-factoid questions, open domain questions or closed domain questions, or simple questions versus like more complex or compositional questions. And for the answer type, it can also be like a short segment of text, or a paragraph, or document, or list, or even the yes or no questions. So just have in mind that there are many different types of question answering problems, and all these problems may require very different techniques or different data, or even different evaluation metrics to evaluate all these different problems. And the question answering has enabled a lot of the useful real-world applications. For example, today, if you just put in a question in a search engine like Google, that, for example, you can put in a question like, where is the deepest lake in the world? So you can see that the current system basically can find like a short a snippet of text, including like Lake Baikal in Siberia holds a distinction of being both the deepest lake in the world and the largest freshwater lake, blah, blah. And then it can actually pinpoint the correct answer, which is actually a concise answer, which should be Siberia. And those kind of systems are also able to handle like more complex questions, like how-to questions. I guess this is probably a question that everyone currently cares about. So the question is, how can I protect myself from COVID-19? So there isn't really a simple and short answer to this question. So you can see that the system actually returns a very long paragraph, including the best way to prevent illness is to avoid being exposed to this virus. And to help prevent the spread of COVID-19, you can do the following. So actually, this paragraph is actually a summary from this CDC article. If you just click this link and read through the article. So this is also one type of the question answering problem. And now this is a survey of the use cases for the current digital assistants such as Alexa or Google Home. So according to this survey result in January 2020, which is 1 year ago, so you can see that people actually really like to ask questions on this digital assistants. So you can see that ask a question is actually the second most used case, only ranked after the listening to music and before the check weather and set a timer. So question answering has been really useful in this digital assistance. And another very famous example of the question answering system is this IBM Watson question answering system. So in 2011, so this IBM Watson QA system has been shown to beat 2 national Jeopardy champions in answering Jeopardy questions. So this is part of this like a historical event, at least in the NLP history. So if we look at the inner working of this kind of system more closely, so you can see that it's actually a very complicated and a highly modularized system. So the system is built on both the unstructured text and also the structured data. So by looking at the system, if you go from the left to the right, you can see that this system consists of the 4 stages, including the question processing, the candidate answer generation, and the candidate answer scoring, and the confidence merging and ranking. And then if you look at each stage, you can see that there are many different NLP techniques that have been actually included in this complex QA system, including like question classification, parsing, relation extraction, coreference. So it's actually, there are really lots of the NLP modules that have been included. And this system has been over 10 years, actually exactly 10 years now. And this actually represented the state of art like 10 years ago at that time. So we know that this class is about deep learning. So today, deep learning has completely really transformed the landscape of the question answering systems. So there's no doubt that we can say that almost all the state-of-the-art question answering systems today are built on top of the end-to-end training of the deep neural networks and the pre-trained language models such as BERT. So today in this lecture, we're also going to learn a lot of these deep learning models for question answering. And this statement is probably also true for almost all the NLP problems that we can see today. But we can also argue that question answering is probably one of those fields that we have seen the most remarkable progress in the last couple of years, driven by deep learning. So in this lecture, I will be mostly focused on focusing on the text-based or textual question answering problems. So basically, we are trying to answer questions based on the unstructured text. So before I get started, I jump to that part. I also want to quickly point out that there are many other really bigger question answering problems, and each of them can be really like a big subfield in NLP, and they actually have very different challenges and also model designs. So one bigger class of this question answer problem is this knowledge-based question answering. So basically, we want to build question answering systems to answer questions that can answer questions over a very large database. So to solve this problem, some approaches need to take this question and convert this question into some kind of logic forms. And this kind of logic forms can be executed against this database to give you the final answer. And another class, bigger class of the question answering problem is called visual question answering. So it's basically you need to answer questions based on the images. So this problem basically requires both understanding of the questions and also images. And there is actually a very active field between the computer vision and NLP. So if you are interested in this type of problems, I encourage you to check out these problems, but I'm not going to dig into these problems today. Okay, so next I'm going to start with the part 2, reading comprehension. I just want to quickly check if there are any quick questions I can answer before I get start the part 2. Yeah.
No, I think we're good to now.
Okay, so yeah, so let's talk about the reading comprehension then. So reading comprehension is a basic problem that we want to comprehend a passive text and answer questions about the content. So it's the input of this problem is basically a passive text, a question, and the goal is to return the answer that actually can answer this question. So here is one example. So let's take, so here is a passive text. And we want to answer a question. The question is, what language did Tesla study while in school? Okay, so I'm going to pause like 5, 10, or 10 seconds and see if people can find the answer to this question based on this passage. Any guess? Okay.
People guessed German.
Yeah, German is correct. So the answer should be German. So basically to answer this question, so you need to find this sentence like, in 1861, Tesla attended this school where he studied German arithmetic and religion, and only the German is the language. So the answer to this question should be German. Okay, here is another example. Again, another passive text. And the question is, which linguistic minority is larger, Hindi or Malayalam, I think, yeah. 5 seconds. Okay, so the answer to this question should be Hindi. So this probably is not a very hard question for humans. It's actually a pretty hard question for machines, because to get this question correctly, so the machines basically need to understand that for the Hindi, like 3.3% of the population speaks Hindi, and only like 1.27% speaks Malayalam, this language. And then also compare these two numbers and found, okay, so 3.3% is a bigger number. So the answer should be Hindi to this question. Okay, so next I'm going to talk a little bit. So why do we care about this problem? So why do we care about the reading comprehension problem? So besides that, it actually drives many useful real-world practical applications. So as I already showed some examples at the beginning, I think there are also 2 other key reasons. So the first reason, so besides applications, the first reason is, so reading comprehension has been also viewed as a very important test bed for evaluating how well computer systems understand human language. So this is really just similar to like how we humans actually test a reading comprehension test to evaluate how well we actually understand one language. So this is also the way that we actually pose questions to test the machine's language understanding's ability. So this actually has been formally stated in back in 1977 by Wendy Lambert in her dissertation. So she basically the saying is, she said that since questions can be devised to query any aspect of text comprehension, the ability to answer questions is the strongest possible demonstration of understanding. So that's why reading comprehension can be a very important test bed, because we can design very complex questions to test that. And also, I think there's another interesting and important reason that reading comprehension is important. So in the recent few years, some researchers actually found that, okay, so for many other NLP tasks, that we can also reduce them to a reading comprehension problem. So I'm going to give you two examples. So one example is the reading information extraction. So basically, if we want to, so given a person like subject Barack Obama, given a relation educated at, so we want to fill in this question mark and figure out, okay, where Barack Obama was educated at. So one way to solve this problem is basically trying to convert this relation into a question. So where did Barack Obama graduate from? And taking a relevant piece of text, and then by applying a reading comprehension problem, then basically we can find out extract the correct answer should be Columbia University. That is also the output of this information extraction system. And another example is actually called semantic labeling. I'm not sure if I've learned this in the class yet, probably not, but basically the task of the semantic labeling is trying to taking one sentence and trying to identify the roles for different verbs, at least for verbs in this case, in one sentence. So basically trying to, given one sentence, or given one verb finish, trying to figure out like who did what to whom and when and where. So by trying to, so the goal is to try to figure out all these like roles with respect to the verbs. So one way to solve this problem is by converting all these different roles into questions, such as who finished something, what did someone finish, and what did someone finish something else. So by converting all these kind of like semantic relations, we can also apply the reading comprehension problem and give you the correct answer. So this is actually a very interesting perspective that reading comprehension can be actually very universally useful to many other NLP tasks. So next, I'm going to introduce this like a Stanford question string data set called SCOT. So if you're going to do the default final projects, you will need to use this data set. So Stanford question answering data set is actually a supervised reading comprehension data set. So which consists of 100K annotated passage and answer question answer triples. So here is one example from this data set. And I just want to say that also one important thing to have in mind is that so this data set consists of the 100K annotated examples. And this kind of large scale supervised data set is also very key ingredient for the training the effective neural models for reading comprehension. So after the SCOT data set, many other like later data sets have been also collected basically around this size, or around like 100K. So 100K is actually very important to train these neural models. So for this data set, so the passages is like a single passage, a single paragraph selected from the English Wikipedia, which usually consists of like 100 to 150 words. And the questions are crowdsourced, basically like from the mechanic Turkey. And there is a very important property of this data set is that each answer is a short segment text, or we call it span in the passage. So as you can see from this example, so here are 3 different questions, and each of these answer can be actually found as like a short segment text in the passage. So this is actually an interesting property, and it's also important property of this data set. But also just to caveat that this is also a limitation, because not all the questions can be answered in this way. So only the questions that that you can find the answer as a span in the passage can actually be included in this data set, basically. But today, so this data set had, yeah, I forgot to say, so this data set was collected in 2016 by several researchers at Stanford. So it's called Stanford question answering data set. Today, like after 4 or 5 years now, so SCORE still remains the most popular reading comprehension data set. So it's actually a very clean and a high quality data set, but it's also not a very difficult data set. So today, basically the SCORE data set has been almost solved. And the state art already exceeds estimated human performance. And I also want to quickly mention the evaluation for this Stanford question answering data set. So there are basically 2 evaluation metrics to evaluate how well a system can do on this data set. The 2 metrics are like the exact match and the F1 score. So the exact match is basically just a binary indicator 0 or 1. Basically measures whether the answer can actually be exactly matched to the gold answer. And the F1 score basically can measure kind of some partial credit. And to do the evaluation, so basically for the development and testing set, there will be like 3 gold answers collected, because for some questions, there might be not just one unique answer, so there could be multiple plausible answers. And the evaluation matrix basically takes a predicted answer and compares the predicted answer to each gold answer with some kind of like some articles and also the punctuations included. And basically you can compute the exact match score and also F1 score by comparing the predicted answer to the gold answer. And then finally takes the max scores. And because there are many different examples in the dev or test set, and then finally we just take the average of all the examples for both the exact match and the reference score. So by using this evaluation metric, the estimated human performance is by the researchers at that time, estimated by the researchers at the time, is the exact match score is 82.3%, and the F1 score is 91.2. So here is just a quick example. So here is the question: what did Tesla do in December 1878? And there are 3 plausible answers. So you can see that the first 2 answers are the same, left grass. And the third answer is left grass and serve, I think the title here, all relations with his family. And then if you found the prediction is span, which is left grass and served. So you can see that there isn't an exact match score between the predicted answer and any of the gold answer. So the exact match will be 0. And the F1 score will be taking the max. I'm not going to talk about how these are computed. So I suggest you check out the original paper. So by computing these scores and taking the max, and the final is the F1 score will be 0.667, which is the F1 score for this predicted answer on this data set.
So Danqi, one question you might answer is, so if you can do other tasks like named entity recognition or relation extraction by sticking something on top of BERT and fine tuning for it, or do it as question answering, does one or the other method work better, and by how much?
That's an interesting question. So I haven't really seen that. Okay, so there has been some claims that okay, all the tasks can be converted into question answering tasks, but I'm not sure there is really like a very fair comparison. Let's say NER and entity recognition, and by really converting that into question answering tasks. So I don't have the answer to that. So the current state of art NER system is still trying to just train a sequence tagger on top of the BERT. So yeah, I don't really have a precise answer to that. Should I continue? Okay.
Yeah.
Okay, so next I'm going to talk about how to build neural models for reading comprehension, in particular, how we can build a model to solve the Stanford question answering dataset SCORE dataset. I also want to just quickly mention that because there are many different papers, they actually use like different notions to refer the same thing. So starting from, so I'm going to use the passage, paragraph, and context, and also question and query basically interchangeably. So they are basically referred to the same thing because different papers use also different notions. So I just want to quickly mention that. Okay, so how can we build a model to solve this problem? So let's first formulate this problem. So the input of this problem is let's take a context or a paragraph. So C, which consists of the n tokens, C1 to Cn, and also we take a question Q, and the question consists of m tokens Q1 to Qm. So n could be something like around 100 to between 100 and 200 for Scott, and m would be much shorter, would be something like 10 or 15. And because the answer has these constraints, the answer must be a second text in the passage. So the output can be just written in this way, so that we are going to predict a start and end. So start and end will be range, be within the range between the 1 and the n. So it's basically just two checkpoints, two endpoints of the answer. And so Scott has been collected basically in late 2016. So after 2016, there have been like basically two families of the models, neural models to solve this, solving this like Scott data set. So the first family, basically like there are a lot of models that came out during that period between 2016 and 2018. So this family of models basically are LSTM-based models with attention. So these are like just like a list of the representing models that came out during that period, and including some work that I did when I was a PhD student at Stanford. And the second class of models I put here is really there's a divide here before the BERT and after BERT. So after BERT came out, so almost all these reading comprehension models were built on like how to fine tune the BERT models. Not just BERT models, so I put the BERT-like models, so pre-trained language models, and for this kind of reading comprehension problems. So here are like the illustrations of these two families of the models. So on the left is like LSTM-based models with attention, and on the right is the BERT model, and then we need to fine-tune this model for the question for the reading comprehension task. So I know that so my plan today is first try to talk about this LSTM-based models. So I'm going to spend a little bit more time on this part because I know that for the default final project, you need to implement this model from the scratch. So I'm going to walk through how to build this model like step by step, and hopefully that you can have a good understanding of how this model works. And then I'm just going to briefly talk about how to build use the BERT models for the reading comprehension. Okay, so before I start talking about these LSTM models, I know that you have already learned this sequence-to-sequence models with attention for machine translation. So I want to draw some connections between the machine translation problem and the reading comprehension problem because they really share a lot of similarities. So first, so in the machine translation model, or this like sequence-to-sequence model, there is a like source and target sentence. So basically, two sequences. So, but in our case, in this reading comprehension case, that we also have two sequences. One is a passage, and another is a question. But the length could be a slightly imbalanced because the passage could be much longer than the question. But there are essentially also two sequences. And so in the reading comprehension, we need to model like which words in the passage are most relevant to the question. And if they're relevant to the question, so it's also relevant to which set of the question words. So this is basically a very key important thing that we actually need to model. And this is actually very similar to the machine translation model that we need to model which words in the source sentence that actually are most relevant to the current target word. So you can imagine that attention will be also really the key ingredient here, that just like the sequence-to-sequence model, we need to model the attention between the source sentence and the target sentence. We also need to model the attention between the passage and the question. So this is actually very similar. So something that's actually not very similar is for the sequence-to-sequence model, we need to build like a decoder, autoregressive decoder to generate the target sentence word by word. But in this reading comprehension problem, we don't need to really generate anything. So we just take the passage and take the question. So at least for the Scott data set, we just need to train two classifiers to predict the start and end positions of the answer. So that part is actually simplified. So we don't need to train the decoder to generate the target sentence. Okay, so next I'm going to talk about this model called BiDAF. So it stands for bidirectional attention flow for machine comprehension. So it was proposed by Minjun Seal and other folks in 2017. So it remains at least before the BERT came out, it remains one of the most popular reading comprehension models and achieved very good performance at that time, at least on the small data set. So you can see that this model seems to be pretty complicated, but if you look at this model from the bottom to the top, it actually can be decomposed into many different layers. So the next, I'm going to just dissect this model layer by layer and talk about, okay, what these layers are actually doing and how we can really build this model from the bottom layer to the top layer, and then finally train this model in an end-to-end way. Okay, so the first part is actually the bottom three layers called character embedding layer, word embedding layer, and the phrase embedding layer. So I just put them together, call this as an encoding function. So the idea here is that, okay, let's take the context query or the passage in question. We need to encode them separately. So to do this, so this model basically proposed to use a concatenation of the word embedding as well as the character embedding for each word in the context and the query. So for the word embedding is straightforward. So if you have learned the word embedding, so you can just look up the word for this word like Seattle, just use the glob embedding as a representation for this word. And for the character embedding part, so you basically need to represent each character in this word like Seattle, and bypass this to a convolutional neural network with some kind of max pooling operations. And then finally, you can just get one representation at the top. And then you just concatenate the word embedding and the character embedding. So these character embeddings have been shown effective to improve the representation for the unseen or the real words. So mathematically, you can see that for each word in the context of the query, we can just represent this representation as blobs of the embedding and the character embedding, and then we just concatenate them and pass this to like a highway network. So I don't write the function here. So so you can just look at the original paper. And the second part, so after we encode each individual word, so on the next we are going to pass this like word embedding into two separate bidirectional LSTMs to produce these contextualized embeddings for both the context and the query. So let's look at this equation. So we take the representation of this word, and we just basically, this is like a one LSTM model from one direction, and this LSTM model from another direction. So we just need to concatenate the two hidden repetitions for two directions, and finally we can get a contextualized repetition for each single word in the context. And we can do the similar thing for the question repetition. I also want to quickly mention, because I mentioned the sequence-to-sequence model. The sequence-to-sequence model, we cannot really do this bidirectional LSTMs for the two sequences. Again, like because the decoder is an autoregressive model. So that's why the decoder is usually just implemented as a unidirectional LSTM. But because here we don't really care about the generation, so we can just use two bidirectional LSTMs to represent the repetitions. This is actually very important. This bidirectional length is actually very important to capture the context from both the left and right side. Okay, so the next component is the next layer. It's called the attention flow layer. So I just call it attention here. So the idea of attention is trying to capture the interactions between the context and the query. And in this paper, the BiDAF paper, they proposed two types of attention. So the first type of attention is called context to query attention. So the idea is for each context word, can we find the most relevant words in the question, from the query words. So here's one example. So here the context Barack Obama is the president of the USA. So for each context word, we need to find an alignment. Basically find like which words in the question can be actually aligned with this context word. So you can see that both Barack Obama can be aligned to who, and the president is aligned to Liz, and the USA is aligned to United States. So basically for each context word, try to find the most relevant query words. And then the second type of attention is called query to context attention. So it's basically another direction. So here the idea is to choose some context words that are most relevant to one of the query words. Because the context can be very long. So a lot of the context could be just not relevant to this question. So we just run over several examples. You can see that the first thing we need to do is try to locate, okay, which parts of the sentences in this context can be actually relevant to this question. So this type of the query to context attention is trying to capture, so which context words actually can be most relevant to the query, to one of the query words. So for this example, the question is which city is glooming in winter? So because the question is asked about glooming, so you can try to figure out, okay, glooming cities is actually very relevant to this question. And we can also find this in winter, because in winter is also mentioned in the question. So this part of the context words could be also relevant to this question. So this context words could be probably need to capture and in this attention that, okay, this is actually relevant to this question. Okay, so this is actually basically just an intuition of these two types of attention. And this is also why this model is called a bidirectional attention flow, because there is a context to query attention, and there is also like query to context attention. So let me just go through how to actually do this like query to context attention, the context to query attention in this model. So the way they do this is first to compute a similarity score for every pair of the contextualized vector Ci, and for every pair of the question word Qj. So this is actually the output from the encoding layer. So this already is the output from the LSTM layers. And the way they basically just compute a similarity score by taking the Ci, Qj, and also the element-wise multiplication of the Ci and Qj. So they basically just concatenate these three vectors. So the output will be a 6H dimensional vector. And they just multiply this to compute the dot product of another like a learnable vector. And then finally, just this basically can give you one scalar, one number, the Sij, which measures how the similarity between this context word Ci and also this question word Qj. So if I learned the attention before, so this is actually just one choice of this model. So there could be many different ways to define this similarity and similarity scores. So this is basically just one design choice of this model. Okay, so after defining the similarity score Sij, so the context to query attention, again, like which question words are most relevant to Ci. So the way they do this is, so basically just taking this matrix, the similarity score Sij, for each row basically corresponds to like one context word. For each row, they are going to compute the softmax for each row. And this can give us like normalization scores alpha ij, which is a probability distribution over all the question words alpha ij. So this is just really similar to all the attention mechanisms that you probably have seen in this class. So basically, for each context word, taking the softmax over all the question words and get us probability distribution. And then finally, just take the linear combination of the weighted combination of this attention score alpha ij and also the question vector, the Qj, and then finally you can get a vector AI, which is actually 2H dimensional vector. So this contextual query attention basically just try to capture which questions words are most relevant to each context word. So the next part is a query to, sorry, the typo here, sorry. This is actually the query to context attention. So which means that which context words are relevant to some question words. So a lot of context words will be not relevant to this question. So the idea to do this, is for each row of this Sij, they basically just take the math scores over all the question words. And after taking this math score, they compute the softmax over all the context words here. So here the I is actually enumerates over all the context words. And this can give us another attention score beta I, which captures how important this context word is relevant to this question. So after computing this beta I, so we can again compute this like a weighted combination by computing by summing up the beta I and also the context vector Ci, and then finally we can get our vector Bi, which is also another 2H dimensional vector. And the final output of this attention function is actually very complicated here. Is also the design choice of this model. So they take the context vector Ci, and they take the AI from this part, the context to query attention. And they take the element multiplication between the Ci and AI, and also the Ci and the Bi. And then finally, they take the concatenation and it can produce a 8H dimensional vector. Okay, maybe I want to pause a little bit and check if there are any questions because this part is a little bit complicated. Yeah.
I mean, one question is, why is query to context and context to query attention not symmetrical?
That's a good question. Yes. So here, essentially the goal is trying to, because the goal is final goal is trying to find a span in the passage. So the point of this attention function is trying to produce a repetition for each single context word in this context. So that's so we are not trying to generate the question repetitions. Here, the goal is trying to generate the context repetitions. So the difference between these two is like, first is try to see which questions words are relevant to this context word. Another part is trying to figure out which context word can be relevant and which context word can be not relevant. I hope this answers your question. Yeah.
Here's an easier question, sort of on the same topic, which might help. Is there a reason why you use both query to context and context to query attention? Is it sometimes advantageous or okay to use just one?
That's a good question. The reason is, yeah, so I'm going to show some observations starting from this paper. So they basically just find both directions can really help by drawing the context query and query to context. So there'll be some observation studies. So by using one set is useful, but just not as good as using the both directions. Yeah.
Wait, let's see. In the bottom right, we sum over I, so why does the I remain in BI? Is that correct, or is there a typo there?
This is not a typo. So again, sorry. So the output, yeah, I know it's a bit confusing. So the output of this model, this module, is to get a repetition for each context word at the end. So both the output for AI and BI, I is actually enumerate from like iterates over all the context words. So BI will be still just to try to aggregate over all the question over all the context words. But the beta I measures the importance of these context words compared to all the context words. So both AI and BI are actually with respect to the context words. Yes. So you can see that here is basically doing some kind of the element-wise multiplication. So the output of GI will be actually only ranged from the 1 to n, which is the number of the context words. Yeah.
There are lots of questions about this. What is the rationale for the expression for GI? How does one come up with such an expression?
Okay, I don't know. I guess the authors try out a lot of things. And so key point here is trying to understand, the roles of the context to query attention and query to context attention. So I bet there could be many different formulations to do this. I also think the authors have tried many different variants, but this is what they came up at the end. I think that if after we there could be some other ways to incorporate both attention, but it doesn't have to be written this way. Yeah.
I mean, one other question would be in the query to context attention. Why do you do a max inside the softmax?
Yeah, sorry, I should have explained this more clearly. So here again, query to context attention is to try to measure whether the importance of these context words with respect to some answer question words. So so by taking the max for each row in this A matrix, so it's basically trying to see, okay, which question word is actually most relevant to this context word. If this number is still very low, that means there isn't any question word that could be aligned with this context word. So this will just after taking the max, if this number is still very low, that means this context word is not very relevant. So basically, that's why we take the soft max, apply soft max on top of the max.
I know. Do you want even more? Do you want to go on?
I probably should move on. I do have a lot of slides, but I'm happy to answer questions after the ones. Yeah.
Maybe you should go on.
Yeah. Okay, so the last part of this model is actually the easiest, the most simple. So there are two. Lastly, there are two layers: modeling layer and output layers. So for the modeling layer, so again, after the attention layer, they take the key derivation. So basically GI, which captures the tension between the context and the query, and then basically just pass this GI to another two layers of bidirectional LSTMs. And the main reason they do this is the attention layer is basically modeling the interactions between the query and the context. And by passing this to another two layers of bidirectional LSTMs, the modeling layers is basically modeling can also further model the interactions within the context words. So basically the formulation here is, so these are two layers of bidirectional LSTM. By taking the GI as input, and the output will be the MI, which is another 2H dimensional vector for each context word in the passage. Okay, so finally the output layers. So for the output layers, it's basically just two classifiers, just trying to predict the start and end positions. So by doing this, so the first concatenate the GI and MI. So this will be actually a 10H dimensional vector. And by computing the dot product of another vector called W start and this resulting vector, and they can basically get a score for each position in the context. And then you can just apply a softmax. And then this will give you a probability that, okay, what is the probability this position I would be actually be the start position of the final answer string. And they also have something, another classifier to predict the end position of the answer. But they also did something a little bit more complicated. So they actually pass the MI to another bidirectional LSTM here. So they call it M prime I, and they concatenate GI and M prime I. Oh, sorry, this is the typo. So this should be WN. So they compute the dot product between WN and this vector, and this can reproduce all the probability over all the positions, which predicts how likely this position will be the end position of the answer. So by passing the MI to another bidirectional LSTM, the reason is that they're trying to capture some kind of dependence between the choice of the start and end. So you can imagine that start and end shouldn't be too separate. So could be independent predicted, but if they claim that if you add some kind of dependence between the MI and the P start and P end, this can actually perform better. Okay, I'm done with this part describing the BiDAF model. Any quick questions I can answer?
I think you can actually go on.
Okay. Okay, sorry, I forgot to mention this. So, okay, the final training loss will be just by taking these two probability distributions, and is basically just negative log likelihood of the gold answer, the start position of the gold answer and the end position of the answer, and by basically taking the product of these two probabilities but you apply a log, so it's a sum of the two negative log terms will be the final train loss. And the whole model can be just trained in an end-to-end way, from the encoding layer to attention layer to modeling layer and to output layer. So this will be just completes the whole model of the BiDAF model. Okay, so this model is actually achieved like on Scott dataset. It achieved a 77.3 F1 score. So as I mentioned earlier, so these are some ablation studies. They found the both attention in two directions are actually important. If you remove the one direction, the performance will actually drop quite a bit. If you remove the context to query attention, the performance will drop to 67.7 F1 score. And if you remove this part, it will drop to a 4.F1 score. And also the character embeddings can also help. So if you remove the character embeddings, you'll get like basically 1.9 point drop. And on the right of this figure, you can this slide, you can see a very big table. So it's basically all the models that came out at that time between 2016 and 2018. So you can see that BiDAF is here, so it achieved a 77.3 F1 score. And basically all the models are actually in a very similar ballpark. So numbers range from like the highest number here, 79.8, until like after the ELMO was introduced, the numbers have been actually improved quite a bit. So before the ELMO, basically all the numbers are actually kind of similar. So each model actually improved the previous model by like 1.2 points. And here is the attention visualization by to show that how this like similarity score of the attention actually can capture the similarity between the question words and the context words. So here example, the question is where did the Super Bowl 50 take place? So each row is actually a question word here. And each column in this matrix basically indicates the attention score, the similarity score that has been learned by this model. So you can see that on the right is basically trying to print out or display the context words that have the highest scores. So you can see that the where has been aligned very well with at the stadium Liva, and also the Super Bowl 50 is basically aligned very well with the Super Bowl 50. So this basically really tells that this kind of attention scores can actually capture the similarity scores pretty well. Yeah. Okay, so next I'm going to talk about BERT, how to use the BERT model to solve this problem. So I know that you have learned the BERT in the last lecture, so I'm not going to repeat this. So very quick. So BERT is basically a deep bidirectional transformer encoder pre-trained on the large amounts of text, and is trained on the two training objectives, including mask language modeling and the next sentence prediction. And this model has a lot of parameters. So the BERT base has like 110 million parameters, and the BERT large model has 330 million parameters. So okay, so how we can actually use BERT for reading comprehension? So it's actually very easy and very straightforward. The idea is to take the question as a segment A. So in the BERT pre-training, there are like two segments for the next sentence prediction task. So when you apply the BERT on the reading comprehension task, you basically just take the question as a segment A and take the passage as a segment B. And then finally, the goal is trying to predict two endpoints in segment B. So here's one more concrete example. So question is how many parameters does BERT large have? So you can see that, so they basically just take the question here and then take the passage here. And by putting in the COS token and the ACEP token, and by just concatenate the question passage tokens. And also for the question side, you just need to pass the A segment embeddings. And for the passage, you just need to put in the segment B embeddings. And then finally, the training loss is also the same. So you basically just try to maximize the sum of the negative log likelihood of both the start and end positions. But here, the way that they compute the start and end probability is slightly different. So it's actually very straightforward. So you just pass this input rotation into BERT. And the BERT can give you the hidden vector HI that can actually represent the hidden vector that corresponding to the context word CI. So you can just introduce another two vectors, W start and Wn, by computing the dot product and then apply the softmax. Then you can just give you a very similar to what we had before. But here is the HI is just the output from the BERT encoder. And then we are training these two W start and Wn to for these two probability distribution P start and Pn. Okay, so for this model, so all the BERT parameters, that is actually a very large number. If you use BERT base, it will be 110 million parameters, as well as the newly introduced parameters H start and H end, which is, if you take the BERT base, the hidden side will be 768, so it's only like 1,500 new parameters. They will be just optimized together jointly for this training objective L. And it actually works really, really well, this model. So if you just take this BERT model, and by just optimizing all the parameters together, it can give you very high performance. I will show you in a minute. And even if you use the stronger pre-trained models, more than like the stronger models than the BERT models, they can even lead to better performance on SCORD. And the SCORD has also become a standard data set for testing this kind of pre-trained models. Let me show you some numbers. So again, human performance is 91, and BiDAF is 77.3. And if we just do this fine-tuning model, so BERT base can give you like 88.5, BERT large can give you 90.9. So you can see that this is a huge jump from the BiDAF model to the BERT models. And then finally, if you see even the latest pre-trained language models, include the XONet, Robota, or Albert. So these models are either like bigger, or these models are trained on bigger corpus, or the model size are bigger. So basically, these models can give you another like 3-4 point F1 score compared to the BERT large model. So this is already way higher than the estimated F1 score. So this just works really well. Any quick questions?
I think this may be okay.
Okay, so yeah, I guess I went a little bit fast for these BERT models. But next, so I want to also do a bit of comparisons between the BiDAF models and the BERT models. So BERT model has many more parameters. So it's like either like 110 more million or 330 million parameters. But BiDAF has only like 2.5 million parameters. And the BiDAF is built on top of the several bidirectional LSTMs, and while BERT is built on top of the transformers. So transformer means that there isn't any recurrence structure architecture, so the transformers are much easier to parallelize. And a very key difference between the BERT models and the BiDAF models is BERT model is a pre-trained, while BiDAF model is only built on top of the GLOB vectors, which is the pre-trained, and all the remaining like parameters need to be learned from this SCORD data set or the other supervision data set. So here is very clearly that pre-training is a game changer here, that pre-training basically can just change everything and also give you a very large boost in terms of the performance. But also I want to raise another question. So if we don't think of this like pre-training, this like BiDAF model and BERT models are really fundamentally different. I don't think so. So below is actually my argument. So let's try to see how these two models are actually connected, especially in terms of model design. So BiDAF model, essentially they're trying to model the interactions between the question and the passage, right? So both the question to passage and the passage to question. And the BERT model, essentially they're trying to use a self-attention on top of the concatenation of the question and passage. So this is a transformer model. So if you take the question, the passage, so this is a question, this is a passage, and then you apply many different layers of the self-attention. Essentially, this self-attention is able to capture the attention between the context words, the attention between the passage words and the question words, and the attention from the question to the passage side, and also the attention from the question words to other question words. So compared to BiDAF, BiDAF is trying to model this part, but the BERT model essentially can capture the attention between all these four parts. And actually, after the BiDAF came out, so this is also before the BERT came out. So people have been also showing that if you just add a self-attention layer for the passive side, so basically you're trying to explicitly model this attention between the passive words and passive words to the BiDAF. This can also improve the performance. So you can see that these two models essentially really just trying to model the attention between the passive question and also the attention between the passive words and the passive words. And this is actually what exactly the BERT model is doing. Okay. So if there's no further questions, so at this point, I'll talk about BERT models can do really well on this kind of reading comprehension data set. And we talk about the pre-training can really change the performance, can be a game changer in reading comprehension.
I could put in one, Danqi, I could add one question first. People wonder whether you can do well with a transformer that isn't pre-trained, right? If you tried to build a question answering system using a transformer rather than LSTMs, but no pre-training, does that work?
That's a good question. Yeah, it works, but you probably cannot really build a model as big as like 110 million parameters or 330 million parameters models. So actually there's a model between the this like family of the LSTM models and BERT models called QANet from Google. So QANet is actually built on top of the transformers without real pre-training. So that model actually can perform better than the BiDAF models and other models, but it actually underperforms the BERT models quite a bit. So just check it out, called QANet. Okay, I will just continue. So, yeah. Okay, so given pre-training has been so important. So next I want to quickly talk about, okay, the question here is that, can we actually even design better pre-training objective for reading comprehension or question answering? And the answer is actually yes. So this is actually work I did with Mender Joshi and other folks like 1 year ago called Stanford. So think about this. So for the SCORD and a lot of extractive reading comprehension data set, the goal is trying to predict the answer span from the passage as a question. So as an answer to this question. So there are two key ideas being proposed in Stanford. The first idea is that instead of using only the masking of individual words, we propose that we want to mask a contiguous spans of words in the passage, because the final answer will be just a segment of text in the passage. So we are trying to mask out all these possible answer spans from the passage as a pre-training objective. And the second idea proposed in Stanford is that because at the end of because we want to predict answer spans, so we actually essentially trying to predict two endpoints as an answer. So the idea here is that, can we try to compress the two endpoints of the answer span can we try to compress all the information in this span into the two endpoints? So here the idea is that, here let's think about this. If we mask out the full words here, and can we try to use the two endpoints here in this figure, like X4 and X9, to predict all the words in the middle? So essentially we are trying to take the two endpoints and also the position, some kind of position encoding. And then finally, we are going to try to predict all the words in this span. So this is why it's called Stanford. So I encourage you to check out our paper. And this actually really helps a lot, at least for the question answering data set. So as you can see from this figure, so this is scored 1.1 and scored 2.0, and these are many other question answering data sets. As you can see here. So the blue bars here, we call it Google BERT, is actually the original checkpoints are released by Google researchers. And our BERT is actually just exactly our re-implementation of the BERT model, but we have been trying to, using the same data, but we have been trying to train this model for slightly longer. So it's actually achieved a better performance than the original Google BERT. So as you can see, the yellow bars here is actually the Stanford. So Stanford can actually greatly outperform the Google BERT and our BERT basically across all the data sets. that really tells us that, okay, even if we are not going to increase the model size, we are not going to increase the data, by designing better pre-training objectives can also go a long way and do a much better job in, at least in the question answering and the reading comprehension data sets. Okay, so I have like several few slides left in this part. So far I have demonstrated that by using BiDAF model and by using BERT models, we can get a very good performance on the SCORT data set. This number has already exceeds even the human performance on SCORT. Does this mean that the reading comprehension is already solved? The answer is of course not. So let me show, so in the recent last couple of years, there's been a lot of evidence showing that the current systems still perform poorly on adversarial examples, or the examples from the out-of-domain distributions. So here is a very classical example. So proposed by Robin Jia and Percy Liang in 2017. So the idea is that they take a passage and take a question, and they're trying to just insert like a random sentence to the end of the paragraph. So you can see that this sentence has like even like a nonsense entity in this context, Jeff Dean here. But this sentence actually has like a great some lexical overlap between the question. It's actually very similar to this question, but actually the numbers have been changed. The antonyms has been changed. And then they found that this kind of adversarial examples can actually very easy to fool the current systems, and the final and makes the system to predict answer to be the Jeff Dean. So here's the table shows that by adding a lot of these adversarial examples, they found that the performance actually drops a lot. This is BiDAF model, so drops from 75.5 to even like 30%. So for even like this kind of attack, the performance will just drop to very low, like 4.8%. So here's another paper that actually just came out in 2020. So there has been a lot of evidence showing the similar things. So today we can build a very good reading comprehension data set on the individual data sets. But this system trained on one data set basically cannot really generalize to other data sets. So the diagonal is basically this table is basically trained the model on one data set and evaluated on the same data set. And for all the other numbers in this table, basically shows that if you train the system on one data set and then evaluate on another data set, the performance will drop quite a lot. So it basically really cannot generalize from one data set to another data set. So finally, this is actually a very interesting result. So this paper is actually the best paper from ACL 2020. It's called checklist paper. So the idea is that these authors basically try to propose some kind of the test cases to check whether these models can actually really answer some simple questions, but with some specific or particular phenomenon. They found that by just come out with some like really simple question, for example, here, Jeremy is more optimistic than Taylor, and who is more pessimistic? And they found that BERT large model trained on SCORT, and this basically can fail this type of test cases 100% of the time. And now here is another table. So you can see that here's another graphic example. Like Victoria and Alex are friends. Her mom is an agent. Whose mom is the agent? And so to get this kind of question correctly, so it has to understand that Victoria actually refers to a female person, and Alex refers to a male person. So this model, this kind of questions also makes the current models, very large model trained on SCORT totally fail on this kind of test cases. Okay, so I have 10 minutes left. Chris, is there any question I should answer at this point? Yeah.
I think you can go on.
Okay, so in the last 10 minutes, I'm going to give you a very, very brief introduction of what is open domain question answering and what we have been trying to do in the last couple of years. So open domain question answering is a problem that, so it's different from the reading comprehension that we don't assume a given passage. So here, the assumption is that we only have access to a large collection of documents. So one example is just taking the whole English Wikipedia, which has like 5 million articles. So we don't really know where the answer is located. And the goal is to return the answer for any open domain questions. So this problem, so there isn't any single passage. So we have to answer questions against a very large collection of documents or even the whole web documents. So this is actually a much more challenging and also more practical problem. Think about this. So this, if you think about the example of Google example I showed at the beginning, so this will be techniques will be very useful in the practical applications. So the term here, open domain, is just in contrast to closed domains that deal with questions under a specific domain. Yeah. Okay, so how can we solve this type of problem? Because for the reading comprehension problem, we just need to answer questions based on single passage. So this is a paper that I wrote in 2017, 4 years now. So it's called, the paper is called Reading Wikipedia to Answer Open Domain Questions, and the system is called Dr. QA. So this paper basically proposed the idea that we can actually solve this problem by using like a retrieval and also a reader framework. So idea is that let's take a question. Okay, so here our goal is try to answer questions using like a very large collection of documents such as the Wikipedia. So the idea is that there's a retrieval and also a reader component. So the retrieval takes in the question and try to find out like a smaller number of the documents that could be relevant to this question. And this reader model basically trying to read through all the documents that this retrieval return and try to find out the correct answer. So formally defined here is that the input is a large collection of documents, D, and the question Q, and the output could be an answer string A. So we can just decompose this problem into, as I just mentioned, the retrieval and the reader component. So the retrieval is basically trying to take the large collection of document D and Q and try to return a set of documents or set of passages. So here, this number K could be very small. Such as like just like 100. So he's basically trying to pull out, find out like 100 passages or documents from like let's say 5 million documents, and finally the reader is basically takes a question and takes this set of the passages and finally return the answer. So the second problem is exactly the reading comprehension model we just learned. So in the 2017 paper we wrote. So it's actually doing a very simple thing. So the retrieval is just a standard information retrieval model. It's a sparse PFIDF information retrieval sparse model. And the reader model is essentially just a neural reading comprehension model I just talked about. So it's basically trained on Scott and some other question answering data sets. So this is really, the idea is very simple, but it's trying to bridge the two things, how to bridge this retrieval and also the reader to do this kind of open domain question answer. So I'm just going to quickly go over some really exciting ideas that has been happening in the last 2 years, basically. So the first idea is that this retrieval part can be also trained. So we can actually even do this kind of joint training of the retrieval and the reader. So here is actually, so this idea has been first proposed in Kenton Lee's paper in 2019 called latent retrieval for weakly supervised open domain question answering. So this part is basically the BERT model for reading comprehension. And this part is basically the retrieval model. So to get this retrieval model working, they also try to use the BERT to encode the passage and also encode the question. And they try to use the dot product between the question repetition and the passage repetition to model how the relevance, the similarity between the question and the passage. But this is actually a very difficult problem because the scalability of this problem, because there are like 20 million passages in the Wikipedia. So it's actually very hard to model this part. But so I encourage you to check out this paper. And also, second paper I want to quickly mention is also a work I did last year. It's called the dense passage retrieval. So the idea is actually very similar to the previous paper, but the idea is that it's actually much more simplified model and a very easy, very simple, straightforward approach. The idea is that we can also really just train the retrieval part by using 2 BERT models, using only the question and answer pairs. And this model can work really well and it can largely outperform the traditional IR retrieval models. If you see this figure, So the blue curve here is a traditional IR approach, like a BM25 approach. And so the other curve, the orange curve, is basically training this kind of retrieval using only 1,000 question answer pairs. So by looking at all these different curves, basically using different number of training examples, so it's actually can largely greatly outperform the traditional IR models. Okay, so again, really, I don't have time to talk about the details of all these approaches. So I just encourage you to check out these papers, and I think this result is really exciting. So here is actually a really nice demo. So the demo is actually hosted at this website if you want to check out. So again, so the database here is the whole Wikipedia. You can see that if you ask a question like who tells Harry Potter that he is a wizard, and in the Harry Potter series, and the system can really find out the correct article should be Harry Potter film series, and then finally give you the correct answer, which is exactly what you have seen from the Google example here. So the answer could be the Ruber's Hagrid, which is actually the person who tells Harry Potter that he's a wizard. So this is exactly the perfect answer to this question. Okay, I'm going to skip this slide. And then finally, very quick. So this is something that came out very recently. That some researchers have demonstrated that maybe you don't even need this retrieval stage. So you can, if you just use a very large language model, you can also just do the open domain question answering. So the way they did this is that I hope that you have learned the T5 model in this class already. So they just take a pre-trained language model T5, and they are trying to fine tune this model by taking the question and taking the question as the input, as the answer as output without any explicit retrieval. And they just fine tune this on a data set, and they find this model can do pretty well at the testing time by just taking the question and directly generate the answer without resorting to any like documents or like a retrieval system. So this is actually very amazing. So this model is also called like closed book QA systems. Okay, the last slide. So this is one direction I'm very excited about. So this is actually a new direction that basically shows that maybe for the open domain question answering, maybe this reader model is also not necessary anymore. So this idea was first proposed by Minjun Xiu in 2019, and we recently wrote a paper called Dense Phrases that try to demonstrate that maybe you don't even need this like a reader model. So instead, we can just encode all the phrases in Wikipedia using some kind of dense vectors. So what you just need to do is just to do this kind of nearest neighbor search in the answer space. You just encode all the phrases in Wikipedia, encode them using vectors. And by taking a question, you can just encode this question using a vector, and then we can just do the nearest neighbor search. And then you can directly give you the answer. So this is basically a new paradigm of this kind of the question answering model. So you don't need you just need a retrieval. You don't need a reader. So a great advantage for doing this is that, so for the BERT reader model, essentially you have to run a BERT model at the inference time. This is actually very expensive. If we just get rid of this reader model, you can just do the similarity search. You can just do the nearest neighbor search without running a BERT model. So this could be very fast and can even run on the CPUs without needing to run like a very expensive deep neural network. And you can still run very well, perform very, very well. Okay, finally, I hope this works. So I actually prepared a demo for this dense phrases. So I want to show you how this actually works. So you can see that when you type this question, like who won the Nobel Prize in Peace in 2014? So every time you just type like a little piece of the input question, and the system can basically just find out the relevant answer and the relevant text passages. And then finally, the answer is actually shows up. It's actually very fast because it's a bit of real time. We don't run the BERT model, so it's just a retrieval model here. Okay, I'm actually done with this lecture. So it's 5:50 now. Yeah. Thanks for joining me today. Yeah.
Thank you very much, Danqi, for that awesome survey of question answering. I guess given that demo at the end, people will want to know whether you're launching your own search engine soon. At any rate, Danqi can stay for a bit to answer questions, but not forever. But today, because of, she doesn't have a Stanford login, we're going to do questions inside Zoom. So if you'd like to ask a question, if you use the raise hand button, we can promote you so that you appear in the regular Zoom window and can just ask questions and see each other. And if you hang around and don't leave the Zoom for more than a few minutes, maybe we'll just promote everybody who's still there into people in the regular Zoom for some bits of discussion. But we'd welcome anyone who'd like to ask a question by asking it themselves at this point. Okay, I've got one volunteer. I've got more volunteers.
Should I read the questions? Should I look at the chat or?
Oh, no, I mean, so there are now 4 people who've been promoted. There are 4 people. I was the first, so maybe he could start by asking a question, and then the other people that we've promoted.
Okay, so thank you so much for the lecture today. My question is mainly like if you use like a model like, for example, BERT, how small can your training data set be for you to get like reasonable results?
So the question is how we can train a reading comprehension model using only a small number of training examples. Yeah, I think this is a really good question. Especially like you probably have heard the GPT-3 model that has shown that if you only use like a very few examples, you can also do the open domain question answering pretty well. So but this kind of model is huge, like what's the number? Like how many parameters I forgot in the GPT-3 model. Yeah, so it's a very large, very huge model. But okay, so basically my answer is that if we can leverage a very large and very powerful pre-trained language model, there is a way that there is a possibility that we can actually do the question answering with with only a small number of examples. And also there are some other promising directions, including like unsupervised question answering. So by using some kind of approach like from the machine, unsupervised machine translation, this kind of idea that can be borrowed and can borrow some ideas from that. Can also work pretty well, reasonably well in unsupervised question answering. Also I have seen a lot of works like basically showing that synthetic QA data sets can also help a lot in boosting the performance if you don't have enough supervised data sets, supervised examples. Yeah.
So my question is, I guess it's kind of interesting that there's not really that strong of a transfer effect between data sets that are kind of ostensibly similar. So my question is, like, has there been any research done on how close, I guess, like the formatting and the semantic content of these question answering data sets actually adheres to the data that like BERT is pre-trained on? And if so, like, has there been sort of any effect found between those similarities or differences?
Is the question asking like whether there has been like some okay, maybe I can just try to clarify a little bit why the current models cannot really generalize well from one data set to another data set. So I actually really believe that most existing question answering data set or reading comprehension data set have been collected from Mechanic Turk. So it's very difficult to avoid some kind of artifact or like a simple clues or superficial clues that easier, let's say not superficial, but some simple clues that for the machines to pick up. So for let's take the Spodas example that, so you can see that actually if you look at the data set more closely, there has been a lot of examples that the question having like a large overlap in terms of the words between the question and the passage. So the model is actually very good at picking up this kind of clues to get very high performance on this data set. And another data set is called drop. So it's basically about the comparison of the two numbers, something like that. So that's the reason that one specialized model that has been trained very well in one data set is very easy to pick up this kind of clues, and it's very hard to generalize this kind of thing to another data set.
What about the natural questions data set? Doesn't that avoid that objection?
Yeah, natural questions would be much better, but there are some other issues. I'm not sure if you have seen that. There's a recent paper called like a trend test overlap paper. So that basically demonstrates.
Can I just interrupt? So natural questions was a data set that Google put out about 1.5 years ago, maybe, where they were actually taking real questions from Google search logs and then finding answers, trying to find answers for them in web documents. Sorry, go on, Danqi.
Oh, I just want to mention, yeah, I think definitely natural questions is a much better data set because the questions are natural, like collected, are real questions that are asking by like users. So it can avoid this kind of superficial the artifact between the question and the passage. But there are some other issues that people like to ask some common questions. So if you just do the random split of the questions into trend depth and test, and there's a recent paper showing that there is actually basically not is inevitable that there is a high overlap between the trend and depth. So if you find this question, if one question that you're trying to test in the depth set or the test set that also already appears in the training set, that is not really generalization, right? Yeah. But this is more on the like open domain setting, not in the reading comprehension setting.
Yeah. Do you want to ask a question?
Yes. So you mentioned that in the last part of the presentations that the reader model may not be necessary, and you presented the dense phrases which can also work well on CPUs. So do we know how well it performs on the question and answering datasets? And compared to other models, including BERT and those that runs on GPU, of course.
Yeah, I just encourage you to check out this paper. So this model is basically performs on par with like the dense passive retrieval retrieval model. So it performs on par with all the retrieval reader models. But it's actually right now so I skipped one slide. So right now the state of the art is actually dominating by this kind of dense passive retrieval plus the generative model. So this so using a T5 model plus a dense passive retrieval, this is actually perform really well. So I would just say so dense phrases can work basically similar in this block, but compared to this kind of generative model, is still like a few points behind. Yeah.
Okay, and what is the kind of the intuition behind the dense phrases, apart from like the answers are probably in close proximity, and what if the data sets has answers to a specific question like very far from the actual information? Like say the answers to the question may not reside in close proximity to the words in the question.
So let me just clarify this. Okay, the goal of this project is trying to index all the phrases in the Wikipedia. So, and these kind of repetitions are built using the training set of the question answering data sets. So the assumption is still the distribution of the examples in the dev and test set will be similar to the training set for sure. Does this answer your question? Like, so basically, we're still trying to consider all the phrases in Wikipedia, and at test now we just take the question observation and try to compute the dot product.
Okay. So if we use say a different data set that does not present the information using the structure presented in Wikipedia, then this model may not work as well as the Wikipedia.
So what do you mean by structure represented?
So say if we lean more towards structures like the passages we see in standardized tests, where the answers to the question may not be in close proximity to where the information was first introduced.
Oh, no, so the answer doesn't have to be seen in the training set. So basically the goal is to taking the training set, train an encoder for the phrases. And by using, and then we apply this encoder to all the phrases, a lot of like 6 billion phrases in Wikipedia. So the model is definitely able to generalize from the training set to all the phrases in Wikipedia. So it doesn't have to be seen in the training set. Is this what you're asking?
I see. Okay.
This is actually it's actually similar to like the retrieval or the dense passive retrieval. So you still like try to train a passive repetition. Here is the phrase repetition, but the repetition is only trained using the training set of the question answering data sets. But by taking the encoder, and then we are going to encode all the repetitions, all the passages or phrases in Wikipedia, and then we can expect that this repetition can actually generalize well for the unseen questions. Yeah.
So the question is what if the nearest neighbor search doesn't return the answer?
So why do you think the nearest neighbor? I mean, it always can find something, right? It's just the question is that whether it's close enough or not.
Yes. So the question is, what if in the data says that the answer is not close enough? Then.
Yeah, that's a good question. I don't know. If you really come up with something that is really very far away from all the questions that we have been seeing in the training set, that could be possible. I don't know.
Basically, depend on how the texts are formatted. Then the nearest neighbor search may not work as well as the models.
But again, the question repetition is also returned by a question encoder.
Right.
So,
yeah.
So the question is whether this question encoder can give you something reasonable in that space or not. But I don't know. Yeah. So we have been testing a lot of like random, even the input sentences, or even like the question doesn't have to be a real question. It could be a sentence. It doesn't seem to be a problem so far. Yeah.
Oh, okay.
Maybe we should give a couple of other people a go. And you're allowed to turn your camera on or ask a question if you want. Next person is.
All right. Hi. Thank you for taking the time to teach us. My question is kind of quick. So you mentioned work that brought up a set of relatively simple questions that show how brittle or poor the current models can be, right? I'm curious if that triggered. Yeah, exactly. Exactly. Did that trigger a big change in the community to improve how to evaluate the models? Because they're actually doing pretty poorly on some of those, right?
Yeah. So first, these questions are simple in terms of the wording is very simple. The template is very simple, but they're still trying to test like a negation or temporal relation or reference. So the questions are not. I mean, in terms of the reasoning or the capacity is not that simple. It's just the wording is very simple. I do think, okay, so this paper definitely received a lot of attention in the best paper last year at ACO, the biggest conference, NLP conference. So I think a lot of people are trying to solve this problem. I cannot tell you that, okay, whether we really have a solution to this yet or not. Yeah.
Cool. Yeah. Thank you for bringing this one up. It's really interesting.
Okay. Next is.
Hi, thanks for taking this time. So my question is kind of not relevant, but like to build a robust system of question answering, in what extent can in-context learning help models to be more robust with respect to different domains?
Can you tell me what do you mean by in-context?
Oh, so like basically you provide template generated by BERT, and then instead of directly predicting the classes of text classifications, you just use some word to represent that class and predict the word instead.
Okay. So I assume that you actually refer to like the in-context learning in the GPT-3 work, stuff like that. Okay. Actually, I've been doing something related to that learning recently. But I'm not sure how we can actually use that kind of in-context learning at least for scored type problems. Yeah, so I don't know if that could solve the robustness or not. I even don't know how to use that technique for the question answering yet. Yeah.
I see, thanks. And you also mentioned that we can train a retriever without a reader. So is there a paper about the current attempt to do that?
Yeah, so paper is already out. So just yeah.
Okay. Thanks a lot.
Okay, next is.
Hey, how's it going? Thanks so much for the lecture. A bit of a broader question, sort of about the future of NLP. Do you think that in order to solve NLP, in a sense that you can perform on par with humans on all NLP tasks, it's sufficient to only interact with text data, or do you think we'll eventually need some sort of the sort of experience and common sense that you get only from seeing and sort of feeling the world and having the sorts of interactions that we as humans have?
Yeah, I mean, common sense is definitely very difficult. Even in the context of question answering, common sense is a very, very, very important topic that still remains, I think it still remains unresolved. That's for that part, the answer is definitely yes. And I also want to mention that, okay, so for a lot of the reading comprehension data sets or question answering data set, you're seeing that people start to achieve the human performance. But we also see that how brittle these systems are because, I mean, they cannot regeneralize or solve the easy problems. So all these things need to be solved.
Do you think the current sort of benchmark data sets are maybe a little bit too easy? In the sense that they don't require. Oh no, sorry, go ahead.
Yeah, one point I forgot to say is that there have been a lot of trends recently trying to have like a human in the loop a framework to evaluate these kind of systems. Just try to break the current system, come up with some harder questions. So so that means maybe the current static data sets are not good enough to measure the progress. So we actually really need some kind of dynamic evaluation and also introduce more of these kind of adverse examples or the harder questions or something like that. Yeah.
Are you still game for a couple more questions?
Sure. I don't want to mention it's 9:10 p.m. On the East Coast. Yeah.
Okay.
So next is.
Yeah, thanks so much for the lecture. So in NeurIPS 2020, there was this efficient open domain question answering challenge. And from performance, it seemed like there was like quite substantial decrease versus human accuracy. Probably primarily due to quantization and also some drift that occurred when they were quantizing. So I recently encountered this paper called Learnable Quantizers, which essentially learns like basis representations for the quantizers like jointly with the weights of the network. And while this would be like extremely effective if you were to just like say train from scratch, I was just sort of curious, do you think that like such a there's some way to do this with say a pre-trained BERT model or something like that? I had a few ideas with like beam search, for instance, but I was just I don't see a very clear way of doing it.
Yeah, I don't think I'm really expert to answer that question. I'm not sure if I really have the answer, but I also want to quickly mention that, quantization has been definitely very useful technique to make the model smaller, right? So we have been also exploring the quantization in the dense phrases project recently because of the storage has been still very large. So we have been trying to reduce that storage. Yeah, I'm not sure about the question about the connection between colonization and also pre-training. Yeah, I'm not sure. I have answer to that. Yeah, sorry. Yeah.
Thank you. Yeah, thanks.
Danqi was too modest to mention that she was one of the co-organizers of the Efficient QA shared task. Okay, next question is.
Hi, Danqi. Thanks so much for being here today. So my question is a bit different. So one example you gave that caught my attention was this Alex Victoria example in the checklist. And I was thinking technically Alex wasn't a wrong answer, right? It's gender neutral and there wasn't enough context in the question to determine who it's referring to. So my question is, how concerned should we be about potentially encoding sort of biases into these sort of goal labels or how we evaluate them? Or is that just more of a concern for more open-ended questions?
Yeah, this is definitely very important. Again, like a lot of people are trying to study, okay, how much bias has been encoded in these models and how we can, yeah, I'm not sure if I have a good answer to that. Again, like just I want to say like how to do the debiasing of the pre-trained language models. All these things are very important, and yeah, this is just one. So you're talking about this example, right? So this is just one test case. Yeah, I don't know. Yeah.
Right, yeah. So I guess I'm just a little worried about, who comes up with the test cases, right, and who determines what the right answer is.
Yeah.
Thank you.
I mean, we will have more discussion of toxicity and bias coming up very soon, including actually Thursday's lecture as well as the later lecture. Not specifically about QA though. Okay, next person is.
Great, thank you for the lecture. Yeah, and my question is also related to the open domain question answering. So I was just wondering how much of like the learning side of domain like sort of generalization or like domain alignment techniques can be combined with like the language level like question answering, like to what extent would they work, and like what kind of like language specific design should be leveraged to combine with those to sort of like if we want like higher performance and stuff like that.
It's a question about how to generalize between different domains, or like about how to design open domain QA system for different languages. I'm not sure if you get that.
Right, so I just wondering, so there's like some like learning specific designs like um, domain adversarial alignments and like feature level disentanglement techniques that has shown some interesting performance on other tasks. And I saw that like recently some people also like leverage similar things like for question answering. So I was just wondering like to what extent these kind of techniques can work on language tasks, not just limited question answering, but like mainly for question answering.
Sorry, which work are you talking about? I'm still not sure. What do you mean by disentanglementations for question answering?
So basically, I mean, this is like a little bit more specific for so there is this paper called doing I forgot the exact name. It's sort of trying to like adversarially align two domains by disentangling.
I think I get it.
Yeah.
Okay, so just want to make sure that we are on the same page. So I have seen some work that's trying to learn some kind of disentangle rotations that can better generalize to the different domains or adverse examples. Is this what you're saying?
Yeah.
And the question is whether this technique can be generally applied to question answering.
Yeah, I'm just wondering how to what extent would they work, because I think language has like a lot of like specific things like dependency and other stuff that like these techniques does not like actually take care of. So I was just yeah.
Yeah, I'm not sure. I think we have to try that, but that's an interesting point. Yeah, I don't know. At least for the work that I've seen so far, it all applied or operated at a very simple sentence classification task. Maybe anonymous, maybe that's not correct. So my understanding is that the basic take like an encoder applied to a simple text classification task and take the hidden repetition, do some kind of transformation and make sure that it can learn some kind of invariant features from the hidden repetition, something like that.
Right, yeah, cool.
Yeah.
For your input.
Yeah, I'm not sure. I feel like QA is a more structured task and also handles longer sequences. Yeah, so I don't know if it works unless people have tried that. Yeah.
Cool, thank you. Thank you.
Okay, and then we've got, and maybe we should call this the last question.
Hi, I'm just wondering what is like the intuitive difference between solving question answering with generative models like T5 versus encoders like BERT?
Okay, that's a good point. Okay, so I skipped this slide. So why this model works so well? The reason is actually it's not really about the extracting model versus generating model. The reason is that they actually for the extracting model, so if the retrieval returns, let's say 100 passages, so they have to extract the answer from each of the passages and finally figure out which one is the max has the highest score. But for the generative model, essentially they're trying to aggregate all the 100 passages and their repetitions together and do the generation jointly. Do you understand? So essentially taking the 100 repetitions together and do the joint generation instead of only do the extraction from each of the passages. So I think that is actually the key difference. So that's why this generative model can do really well compared to the extracting models. So I also want to mention that, okay, so if you look at this RAG model, it's actually comparing this DPR and RAG model. So RAG model is already doing the generative model, but they're not doing this kind of aggregation. They're just trying to take a single passage and doing the generation. So the RAG model actually doesn't perform as well as this model. By the way, I also want to mention RAG model is actually not doing better than DPR because this base model, this large model. So these numbers are a little bit confusing. So they're actually basically really on par. They are basically perform similarly. But so the key difference between the generative model and the extracting model is that for generative models, you can actually leverage more input passage together and do the generation. Yeah. Is that clear or not?
Yes. Yeah, thanks.
Yeah, otherwise you should just check out this paper. Yeah. So this paper actually explained pretty well that why this model can work better than the previous generative models. Yeah.
All right. Actually, follow up is, can you use generative models to do simple question answering, like you have a document and like span prediction? Can you use generative models to generate the span, like the words?
Yeah, you can. Yeah, you can definitely do that. Yeah. Oh, so you are talking about this T5 model, not this.
Yeah. So I'm just
I see.
wondering about like if you use encoders, it's like you're finding similarities between their encodings, and then generative models. Are you like remembering the whole question, and you try to retrieve that memory, like when you answer the question?
Okay, so for this model, there isn't any retrieval. So you cannot really find the answer from the question, right?
Yeah.
So this model really has to rely on all the parameters you memorize, all the information. So by just taking this input, it has to just rely on the parameters to infer this answer. So it's actually very hard to. So it's definitely a balance between it's a memory and the generalization problem. Yeah.
I see. So I'm just gonna
say what I like? Is it like when you embed this question, it's embedding it in some space, and then using that embedding, the generator matches that to like 1882. Is that what is going on in there?
Yeah, exactly. Yes. The model has is very large, like 11 billion parameters. So all these the parameters basically trying to memorize a lot of information that has been, because the model has been pre-trained on the text and also has been fine-tuned. So the model has been trying to memorize a lot of information from the text. Yes.
All right, thanks.
Do you want to call it a night, or do you want one more question?
Either way, yeah.
It's up to you.
Sure, I'm happy to take one more question.
Okay, let me just do, one more question from.
Okay, the first question is about how easily are these techniques generalized to other languages? Like, say, languages that are follow quite different grammatical rules, like Chinese, Japanese, or Arabic, or some other languages. Sort of another follow-up question, maybe not exactly your domain expertise, is there's a lot of interest in modeling user behavior, say online searching behavior, browsing behavior, as a sequence using, say, transformers, self-attention. And then you can use that to predict how or can like embed the user as a vector, and then can predict users' actions. How promising do you think that would be? I know this may not be your domain expertise, but there is a lot of interest in extending these question answering techniques or just encoding techniques, embedding techniques to recommender systems. Just want to get your thoughts on that.
Okay, the first question is whether these techniques can be generalized to other languages. I think the answer is yes. And there has been a lot of active research in this direction. But there has been also some concerns that as a lot of models or systems I described here actually require very strong pre-trained language model, and also require lots of training examples for the QA data sets. So that would be actually I would say a bottleneck for many low resource languages, right? So it's very hard to collect so many examples for other languages. If we have, actually, I think the techniques can be generally applied to other languages. There has been also a lot of work trying to do like cross-lingual question answering, stuff like that.